will start today by going through the model checking algorithm for LTL properties in a more detailed way. So, in the last class we had seen that the basic philosophy of LTL model checking was like this, that we create a checker automaton from the negation of the property, we extract a finite state machine from the implementation, and then we check whether the product of these two automata has any run, and the run is an accepting run, where accepting run, as we saw later on, is defined not only by whether it reaches certain states, but the fact that it should reach those states infinitely often. And for that, actually we saw that when you build the tableau or the checker automaton, then let us leaf through this, then every run of this checker automaton is not an accepting run, in the sense that it is possible for the automaton to go round and round in some cycle without ever reaching a state which satisfies the property. So, therefore, our acceptance condition is not that it should reach such states, but should reach certain types of states infinitely often, right. And then we found that when we took the product of that with the finite state machine extracted from the implementation, if there is any path which is an accepting path in the product automaton, then we say that we have found a counter example for the original property, because the automaton was created for the negation of the property, and any run which satisfies the acceptance condition is therefore a refuting run for the original property, right. And if the product does not have any accepting run, then we say that the product automaton is empty, because any automaton which does not have any accepting run is said to be empty. Is that clear so far? So, now let us go into a little more theory behind this, but before we go into that, let us quickly look at some computational facts. Now, if a LTL property has k subformulas, then the checker automaton for it has order of 2 to the power of k states. Okay. So, the size of the checker automata is exponential in the length of the LTL property. Okay. And LTL model checking is p-space complete, right, but it is the algorithms that are there are linear in the size of the implementation. So, the exponential that you see in the LTL model checking algorithms is the exponential in the length of the formula, and therefore, the thing that really hurts us is not not this exponential, but the size of the implementation. So, though it is linear in the size of the implementation, that is the main bottleneck, because the size of the implementation is typically very large. So, this is what reiterates, this slide reiterates what I said just now. Okay. So, efficient compact representation of the state space is one of the key challenges, and also the checker automata grows exponentially with the length of the property. So, when we will have big specifications, this can turn out to be a problem also, but we can always in fact, what we do is we always check properties one by one. So, therefore, that this exponential always remains contained. Now, this is what we are going to look at. We are first going to look at the formal procedure for creating the checker automaton, and for that we will see that LTL properties can be converted to non-deterministic Bookie automaton. And then we will briefly go through the determinization problem of Bookie automata, because if you have a non-deterministic automata, and then how do you determinize that before verification, that is one thing that we will study. There is something very peculiar about the determinization problem of Bookie automata, which warrants independent study of that. And then we will go through model checking, where we will look at algorithms for finding strongly connected components, and we will look at the methodology for tableau construction. And then we will go into CTL model checking, and we will study fixed point algorithms for CTL model checking, and then we will see how LTL model checking can be cast into CTL model checking and solved using a CTL model checker. Okay, so this is the agenda. Now a few definitions. The symbol omega is used to denote the set of non-negative integers, that is omega is 0, 1, 2, this set. Okay. By sigma we denote a finite alphabet. Sigma star, as we know already, is the set of finite words over sigma, and sigma omega denotes the set of infinite words or omega words over sigma. Okay. Now this is the difference between sigma star and sigma omega. This is infinite words. Okay. We write alpha belongs to sigma omega as alpha equal to alpha 0, alpha 1, where each alpha I is a member of sigma. Right. Alright. So given any infinite word alpha, the first symbol in that is alpha 0, the second symbol is alpha 1, and so on. Okay. So we can enumerate these numbers, these symbols, and we will denote by INF alpha as a finite set of letters which occur infinitely often. Remember that the alphabet is finite. Okay, so the number of symbols that we have is finite. Okay, each word is infinite. All right, and INF alpha is the set of letters which occur infinitely often in alpha. Okay, where alpha is a word. So it's the set of set of symbols A belonging to sigma, such that for all I there is some j greater than I, such that alpha j is A. So in other words, that wherever you are in this word, there is always another future position in the word where A occurs again. Okay, so that's another way of saying that A occurs infinitely often. So there is no last A in the word. Okay, wherever you are in the word, in the future you have another A. Okay, so for all I there exists some j greater than I, such that alpha j is A. Is that clear? So INF alpha is the set of symbols which occur infinitely often in alpha, and alpha is a infinite word. An omega automaton is a quintuple like this: Q sigma delta Qi ACC, where Q is a finite set of states, sigma is a finite alphabet, delta from Q cross sigma to the power of Q is the state transition relation. So when we say 2 to the power of Q, this means this is a non-deterministic relation. Okay. So this is the state transition relation. Qi belongs to Q is the initial state, and ACC is the acceptance component. Now omega automata is defined over a set of different types of automata, and those automata differ in the acceptance component, and we will see some automatons which belong to the set of omega automata and which have different types of acceptance components. Okay, so this is a very important field of study in computer science. Okay, the set of automatons which accept infinite words, and within that class we have this omega automata, and again under omega automata there are various types of automata which differ in the acceptance component. Okay. In a sorry, this is a typo. In a deterministic omega automata, this should be deterministic. A transition function Q cross sigma to Q is used. Okay. So please read this as deterministic. Okay. It's just written just the opposite way around. the acceptance component can be given as a set of states, okay, as a set of state sets, or as a function from the set of states to a finite set of natural numbers. We will see examples of this. Okay. So, within the within omega automata, the first one that we look at is the Bookie automata, and as you can see that this quintuple is the same, except that for Bookie automata the acceptance condition is a set F. Okay. How do we what is F? F is a subset of Q. It is a subset of the set of states. Okay. And a word alpha belonging to sigma omega is accepted by A. So, an infinite word alpha is accepted by A if there exists a run pi of A, some run pi of A on alpha satisfying the condition that INF pi intersection F is not equal to empty. In other words, that if you look at the set of infinitely occurring symbols in pi, okay, then that infinitely occurring set of symbols has a non-empty intersection with F. So, in other words, at least one of the states in F has to be visited infinitely often during the run. So, in the run pi, at least one of the states in F is visited infinitely often, right. Then pi is an accepting run of the Bookie automaton. Is that clear? No? Okay, so see INF pi is the set of states which are repeating infinitely often. No, what do you mean by symbol? This is a state set, right? Okay. See, let us go through this once again. A word alpha belonging to sigma omega is accepted by A if there exists a run pi of A on alpha. So, when you give alpha as the input to this automata, it is going to trace some path pi. Okay. INF pi is the set of states which are occurring infinitely often in that. That intersection F should be non-empty. Is that alright? So, that is the definition of the Bookie acceptance condition. Okay. F is the set of accepting states, and Bookie acceptance says that accepting states must be visited infinitely often. Okay. This one tells you that on the input alpha, this automata states traces the path pi, and in pi there is some accepting state which is visited infinitely often. Therefore, this is an accepting run of the Bookie automata. Is it clear now? Is that clear now? Therefore, the language which is accepted by this automata is LA equal to alpha belonging to sigma omega such that A accepts alpha. Okay. Is the omega language recognized by A. Okay. Now, this is another type of automata, it is called Muller automata, and the Muller acceptance condition is like this, that the acceptance condition F is a subset of 2 to the power q. So, it is a subset of the power set of q. Okay. A word, everything else is the same. A word alpha is accepted by A if there exists a run pi of A on alpha satisfying the condition that INF pi belongs to F. Alright. Now what does this mean? This means that the set of infinitely recurring states of pi is exactly one of the sets in F. Right. What is F? F is a set of subsets. Okay. So given all the states that are there, I define a set of states, some subsets of states, right. Some collection of these subsets is F, and what we are saying is that on input alpha, if the automaton goes and gets settled in one of these state sets, in other words it keeps on visiting only these states and no other state, then according to Muller acceptance, this is an accepting run of the automaton. Is that clear? The difference between Bookie automaton and Muller automata? In Bookie automata, the accepting condition is a set of states which must be visited, some member of it must be visited infinitely often, right. Then it is acceptable as per Bookie acceptance condition. Muller acceptance, the path for the input alpha should go and settle in a set of states which is one of the set of states in F, right. So it is going to stay only in that set of states, not going to come out of that. Then this is acceptable as per Muller acceptance, right. With these two types of automata in mind, let us proceed forward. So just remember Bookie acceptance and Muller acceptance. So in a paper in 1983, Woolper, Moshevardi and Sisla, they contributed this theorem which says, given an LTL property var phi, one can build a Bookie automaton A like this, where sigma is 2 to the power of AP, where AP is the set of atomic proposition or variables in var phi, okay, and the length of the number of states in Q is upper bounded by the 2 to the power of the length of var phi. Okay, so remember that the var phi, this mod var phi is the length of var phi, and 2 to the power of the length of var phi is an exponential in the length of the formula, and the number of states in the Bookie automata is upper bounded by that. Okay. Now we will not go through the construction of this, because that is the proof of the theorem, where you show that any generic LTL property can be converted to a Bookie automata. Instead, to understand that what this means, let us look at some examples. So if you have A until B, then this is the corresponding Bookie automata, right. So as long as we get A, we stay here, when we get B, we go here, and then whatever we get, we stay here, right. So if I define this as the accepting state, right, then the A until B, after I get the B, then I keep on in staying in this state, so it satisfies the Bookie acceptance condition, right, because once I reach here, I cannot go anywhere else, I am just here only, and this is the accepting state, right. Look at P until Q until R. So as long as I get P, I can stay here. When I get a Q, I can go here, okay, and then I can get Q, and then when I get R, I go here, okay. From here, if I directly got R, I would have gone here, right. But once I reach this state, again I stay here forever. So again, it's easy to see that when you reach here, you have already got P until Q until R, right. When you reach this state, you already have P until Q until R, because you could have reached here after getting R directly, or you could have reached here after getting P several times and then Q several times and then R, or you could have got Q straight away and then R, or Q straight away and then several Qs and then R. So, for each way in which P until Q until R can be satisfied, you will end up here, right, and then you stay here forever. So, the accepting state is visited infinitely often, right. Now, these two do not actually demonstrate the need for visiting the accepting states infinitely often, right. Like these two are almost like the type of automata that we knew before. Now, when you come to this one, let us see what this says. It says always in the future P and next P, okay. So, P and next P is, you get a P and then you get another P. So, if you get two successive P's, then you have matched this part once, right. And let us say that we define this to be the accepting state. But once you have reached here, you again have to reach some state where P and XP is true. Why? Because you have this always. So, it is not sufficient to get P and XP only once in the path. You have to get P and XP in the path infinitely often. So, then that is guaranteed if we define this to be our F in the Bookie acceptance set. So, if this state is visited infinitely often, that means I am getting P and XP infinitely often, right. Okay. These are all non-deterministic Bookie automata, non-deterministic. This theorem says that you actually end up building a non-deterministic Bookie automata. I did not mention it here. So, these are all non-deterministic Bookie automata, right. Now, is that fairly clear that what is the relationship between LTL properties and Bookie automata? So, we can construct a Bookie automata which the accepting runs of which are accepting runs for the LTL property. Now,
can you explain what is meant by T there?
oh, it is any other symbol, yes, any symbol, true. Now, this is the interesting thing. There exist languages which are accepted by some non-deterministic Bookie automaton, but not by any deterministic Bookie automaton. Now, remember that in our normal automata, finite state automata that we studied, the non-deterministic and the deterministic have the same power. In other words, that any language which is accepted by a non-deterministic finite state machine is also accepted by a deterministic finite state machine, and we have a very clear cut algorithm for determinization of the non-deterministic automaton, right. Now, that is not the case for Bookie automaton, which is a major difference, okay. Now, to see that, just look at this example. This example of course does not prove this result, but it actually shows that where the difficulty lies, okay. But the formal proof is there in the paper. We are not going to discuss that in the class, but let us see this example which shows that there is some automaton which I mean this does not seem to be a straightforward way of determinization of that, right. Now, let us see what this says. This is we want to write an acceptor for the language alpha belongs to AB to the omega, where the number of b's in alpha is less than infinity. So, we want to say that B is not occurring infinitely often, right. A language which accepts all those infinite words over A and B where B does not occur infinitely often, right. So, we can represent that very easily using a Bookie automaton, which goes something like this, that I start with Qi, the initial state, and I stay here as long as I get A or B or A or B, and then after that, after some point I go over to A, I go over to this state F, where only A is accepted, right. Now, you see that those infinite words in which B occurs less than infinitely often, for them there will be some last B. After the last B we will have only A. So, then you go over to this and then stay here forever, right. Now, if we try to determinize this using our standard non-deterministic to deterministic automata transformation, then what are we going to do? We are going to actually the states of the deterministic automata are the subsets of the states of the non-deterministic automata, right. So, that is how we determinize a non-deterministic automata. So, here we can if we determinize it using our classical method, then this is what is going to happen. I will have one state for Qi and the other which has Qi and F together, right. So, two sets of states, right, and as long as I have B, I stay here. When I get a, so now look, this is deterministic. When I have B, I stay here. When I get a, I come here, right. As long as I have A, I will stay here, and then when I get B, I go back here, right. So, if I end up in the, so for every finite word, you see, if you end here, then you have ended with A's only, right. Okay. For finite words, that is what it would mean, that I always end with A's, because whenever I get a B, I end up here, which is not an accepting state. Okay. But for infinite words, we have a problem, because this also accepts the words A, B, omega, okay, which means that A and B both occur infinitely often. That is also accepted here, right, because if you look at Bookie acceptance here, then it is fine if we go around in this loop forever, because the accepting state is being visited infinitely often, right. This state is the accepting state and we visit it infinitely often. So, we can go around and round in this forever. So, it does not, it also accepts words where B occurs infinitely often according to Bookie acceptance, right. So, it does not solve our problem. So, let me reiterate what I said just now. What I said just now is that if you take this non-deterministic Bookie automaton and attempt to determinize it using the same technique as determinization of finite state automata, right, like we used to do in our second year courses, then the problem is that this if we treat this as a Bookie automata, then it also accepts words in which B occurs infinitely often. On the other hand, if you say that that we will apply Muller acceptance here, then what does Muller acceptance says? That the accepting set of states should be such that the automata gets stuck there, right. So, if your run is such that the automata gets stuck in this state, then that is what you want. You want the run to go through this B, 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 A, B, A, B as many number of times, but then somewhere down the line it should reach this state and then never get a B again. So, in other words, you want it to reach here and then stay here only, not come out of this, but that is what is stated by the Muller acceptance, right. So, what is the crux of this whole story? The crux of this story is that if we know a method for translating from LTL to Bookie automata. Then when we want to determinize the Bookie automata, we see that every non-deterministic Bookie automata does not have an equivalent deterministic Bookie automata. So, there are languages which are accepted by non-deterministic Bookie automata, not accepted by any deterministic Bookie automata, right. So, therefore, if we try to determinize that and then take the product and find out whether the accepting states are visited infinitely often, that is not going to work, right. So, therefore, what should we do about that? We, however, we do see that if we change the acceptance condition to Muller acceptance, in this particular case we do see that our desired acceptance is met on the deterministic automaton. Now, let us see what we do about this. So, this is what we are going to study now. We are going to study the method, formal method for building the Bookie automaton B not phi from the LTL property. We will call this the tableau, okay, and we will compute the product of the implementation model M with the tableau, and each state of M is labeled with propositions, each state of B not phi is labeled with propositions. We will match states with the same labels. This is the product computation, and then the product accepted if the okay, we will what is the product of this? The product will be another automaton, okay, which will contain common traces between B naught phi and M, okay. If there is any trace which is common between them, then we have found a counter example. Now, let us see the product, the construction of the tableau. To study the tableau construction, we will first define what is called elementary formulas. Okay. An LTL formula var phi is called elementary if it is a variable belonging to the set of atomic propositions, a negated variable belonging to the set of atomic propositions, or the outermost operator is a next operator. So, these are the elementary subformulas. Before we go into the rules, let us see some examples of elementary subformulas. Right. So, suppose we have the subform the LTL property P until Q, right. So, we will rewrite this as follows. We will rewrite this as Q or P and X okay. Now, see, this is an elementary subformula because it is an atomic proposition. This is an elementary subformula because it is an atomic proposition, and this is also an elementary subformula because it is a because the outermost operator is an X, all right. So, here we will have the elementary subformulas will be P Q X P until Q, right, all right. So, let us see how we construct the elementary subformulas from var phi. So, elementary subformula of var phi is var phi itself if var phi is belongs to atomic proposition. So, if the property is a atomic proposition, then it itself is the elementary subformula. If you have not of var phi, then elementary subformulas of not of var phi is the same as the elementary formulas of var phi. So, not is simply dropped. Okay. So, if you have a disjunction of two properties var phi and psi, then the elementary subformulas of this union elementary subformulas of this gives you the elementary subformulas of this. Okay. For a formula of the type X var phi is a elementary subformula, okay, union elementary subformulas of var phi. So, the elementary subformulas of X var phi is x var phi itself union the elementary subformulas of var phi. Then elementary subformulas of this until this is this one union elementary subformulas of this elementary subformulas of this, right? Okay. So suppose we want to get the elementary subformulas of Fp and Gq. How are we going to compute that? First of all, let us rewrite this in terms of the, we will make this AND as the OR. So, we first use De Morgan, right. So, not Fp, okay, or not Gq, right. Now, elementary subformulas of this is elementary subformulas of this, right, which is equal to the elementary subformulas of, see, not, we do not care. So, it is not of Fp or not of Gq, right. So, this in turn is elementary of not of Fp or union elementary of not of Gq, right. This is elementary of Fp union elementary of Gq, right. Now, what do we rewrite Fp as? Elementary of P or XFP, right, union elementary of this we will write as, now see again here you can rewrite this as not F not Q, right. So, this is going to be elementary of P, which is P union of this, which is XFP, right, union, this is going to, let me rewrite it once again, not Q or, first of all this not is going to get dropped. So, just look at it as F not Q. So, not Q or XF not Q, right. So, we will have P union XFP union Q union XF not Q. Okay, so these become the elementary subformulas. Okay. Now, to create the tableau, we will say we will treat each of these elementary subformulas as a state bit, and we will construct, if there are k such elementary subformulas, we will construct a state space consisting of 2 to the power of k states, alright. Now, so the set of states of the tableau is St, which is 2 to the power of elementary var phi. Okay. So, it is the power set of the set of elementary subformulas. Now the labeling function LT is defined as follows. We will first define labels on those states. So far we have not put in any transitions. We will define labels on those states. So which are the, so sat var phi refers to the set of states, okay, which are to be labeled with var phi, okay. So it is S such that var phi belongs to S if var phi is elementary of var phi. So if var phi is an elementary subformula, then in those states where that elementary formula, the state bit corresponding to that elementary subformula is true, they all belong to sat of var phi. Yeah. What are the set of states? The set of states are constructed based on the elementary subformulas. So if I have k elementary subformulas, right. So let us go back to our example that we had earlier for corresponding the example that we saw in the last previous class, that we had what was the property that we were seeing, FQ, right? Okay, and then we broke it down into Q or XFQ, right? And then based on these Q and XFQ, we had 4 states, remember, in the tableau. Which were those 4 states? We had Q, XFQ as one state, we had not Q, XFQ as another state, and then we had Q not XFQ as one state, and not Q and not XFQ as another state, right. Now we first start by saying that, okay, if var phi is one of these things, say supposing Q, right. So what is sat Q? Let us name these states. So let us name these states as S1, S2, S3, S4. Okay. What is sat of Q? Sat of Q is S1, S4. Right? Why? Because this Q is one of the atomic, one of the elementary subformulas, and therefore I know that this elementary subformula is true here and is true here. It is not true here, it is not true here. So sat of Q is this. Okay. What is sat of XFQ? Sat of XFQ S1 and S2, right. Similarly, sat of not XFQ S4 and S3, right. And what about sat of FQ? See, sat of FQ, now sat of FQ can be written as sat of Q union of set of XFQ, right. Why do we write this? Because Q can be FQ can be satisfied in two ways. One is Q holds straight away, or those states in which XFQ holds, which means that in future Q will hold, right. So, if we get these two, then S1, S2, S4, right. So, that is what this SAT tells us, that SAT of var phi is S if var phi belongs to S and var phi is an elementary subformula. Not of that is defined as var phi does not belong to SAT var phi. So, just a complementary set of states. Okay. So, if SAT of var phi is a set of states, then the complementary set of states is the SAT of not var phi. Remember, the set of states is finite always. SAT var phi or psi is SAT var phi union SAT of psi, and SAT of var phi until psi is SAT of psi union SAT of var phi intersect SAT of x var phi until psi. This is obviously the case, because the states which satisfy this are the states which satisfy psi, and those states which satisfy var phi and satisfy var phi until psi in the future, in the next state, right. Now, this is all defining what are holding at which states. The next thing is to define what is the transition relation. So, where do we put the edges in the tableau, right. So, the transition relation is defined here like this, that the transition relation RSS dash is the intersection of these things, that we put a transition from S to S dash, provided that S belongs to SAT of x psi if and only if S dash belongs to SAT of psi, right. So, from this state S to this state S dash, we will put a transition. Okay. Let us come back to this picture example and first understand what this means. Now, we are looking at XFQ here, right. So, we have to put an edge from XFQ to a state which belongs to SAT-Q, okay, SAT of Q. Which are the states which satisfy SAT of Q? So, this one, okay, to, okay, see this is XFQ, which are the states which are in SAT of FQ? S1, S2, S4, right. So, we must put edges from here to S1, S2, S4. Why did we do this? Because this state had x of psi, where psi is FQ, and we are putting edges to those states which are in SAT of psi, which means SAT of FQ, right. All right. Similarly, look at this one, this is XFQ. So, which are the states in SAT of FQ? S1, S2, S4. So, we need to put edges to S1, S2, S4. Okay. Look at this one, this has x of not FQ. So, which are the states in SAT of not FQ? S3. Okay. So, from here we must have an edge to this. This one is x of not fq, okay, which is the state which belongs to sat of not fq S3. All right. So, what did we do? We looked at each state of the tableau, and whenever we had any property of the form x where psi, we put an edge from the state which has x psi to some state which S which belongs to sat of psi. Okay. So, that is what this picture tells us, that this transition relation consists of those transitions from S to S dash such that S belongs to sat of x psi and S dash belongs to sat of psi. Okay. For all x psi belongs to elementary formulas of var phi. Okay. For every elementary subformula which starts with an x, we do this exercise. Is that clear? Right. Now, having computed the tableau and having extracted out the finite state machine from this, we have to find out the intersection and the emptiness. Right. This is something that we will study in the next lecture, that how do we compute the emptiness of the product automaton. Alright, there are some algorithms for doing that. Remember that the acceptance is still Bookie acceptance. It is not just reaching a particular state, but it is reaching accepting states infinitely often. We will see how we do that in the next class.